All right. Okay, so again, guys, we're going down to our BFF graphs. I don't know where that chair went. I think review station. All right, so we're on our BFF graph. So I did quadratic, and I did the quadratic one yesterday, and then I also did the exponential one yesterday. So you already have those two examples down. I asked today if anyone had any specific ones, and so I was asked about sine, which I think is a good one because it's similar to cosine, and the greatest integer one. So we're going to do those two together, and then we'll get into today's notes. Cool?
Is the greatest integer one the dumb one?
Yeah, it's one of the dumb ones. I really hate this one. So the greatest integer one is like a stair step one. So did you guys look at any of them and be like, what is this like weird stair step graph that we're supposed to know? I think it's dumb. And having a math major, I never have ever studied this graph. Like that's why I think it's so dumb. It's like no one talks about this graph. So greatest integer. So this is on the back page, the middle graph on the very, very back page. What happens here is it's just no decimals. It's all whole numbers. So we're just like stair stepping the entire way for a whole number. It starts with a closed circle and then it ends with an open circle. And we'll start at 0 to 1 so that we can kind of center our graph. Okay. And then the equation for this is literally INTX. Because INT. And there's a button you can put on your calculator to do the integer there. So we could do that if we wanted to. I think, again, it's stupid. So I'm going to 0, 0, and I'm putting a closed circle. And then I'm doing like a little dash until I get to 1, and then there's an open circle. Then I'm going to jump up to 1, 1, and do a closed circle, dash, closed circle on 2, 1. Keep going. I'm only going to do like 3 or 4 of these and call it a day. And then I'll do it in the negative direction too. So I'll go close circle, open, close, close, open, all that fun stuff. I don't need to do it the entire length of the graph because it's just going to all work out to be the same thing. And I can kind of assume what's happening. Okay. So what's weird here is the domain range and kind of the numbers that we get to use because we're not using any decimals. So we kind of have to keep that into consideration. Domain, you technically have all of the x's covered. So if I were to think about all of the x's, I have a closed circle and then I have an open circle, but immediately above it's another closed circle. So we're hitting every single x here, even though we have all these open circles. So my domain is still negative infinity to positive infinity. However, range, we don't have any fractions, right? All of our y's, there's like a blank spot in between them, like right here and right here. There's nothing in between, like in the fractional part. So to write the whole numbers, you can either, or this is integers, I guess, you can write the integer sign, which is like a fancy z, or you can write it as the set of these numbers. We'll do brace, ... -3, comma -2, -1, 0, 1, 2, 3, and then we'll just do ... dots again.
So how do you want to do that?
Because I'm not doing any of the decimals here, this is literally the only one that will have this.
Okay.
Mm-hmm.
You think I should put this on the test?
No, because I think it's so dumb.
Oh.
Now, other ones, yeah. Like I could test you on the quadratic and ask you domain range, all that fun stuff. I will never put this one on it because I think it's stupid. Yeah, Andrew.
What's that thing you put for the or?
It's it's a Z. So I drew it like it's a fancy Z, but I drew like the first part and then I retraced the second line to make it look like that.
What's it?
That means the set of all the integers. So you know how you do like real numbers like that?
Yeah.
This is what the set of the integers is. Unless you take abstract algebra, you'll probably never use that. All right, continuity. Is this continuous? No, because I had to pick up my pencil literally every time, right? I had to do a lot of picking up my pencil, not continuous. Now, as I go across the page from left to right, is it increasing or decreasing? Increasing, does it ever decrease? No. So for increasing, I can still write INC, and I'm just going to say negative infinity to positive infinity because it's all of the x's. All of the x's are increasing. Symmetry is no. Boundedness is also no, because it keeps stair-stepping up and up forever, and it could go down in the opposite direction forever. There's no extrema here, because there's no point that's higher or lower than any other point. There are no asymptotes. And then let's do our end behavior. So let's go, as x approaches negative infinity, what does y do? And as x approaches positive infinity, what does y do? In this case, the y is just approaching negative infinity as my x's get smaller, and it's approaching positive infinity as my x's get bigger. So it just matches what we're doing. It's kind of like the identity graph, like where I'm just increasing in both directions, or I'm just going as far down as possible over here. So when x approaches negative infinity, so does y. Y also approaches negative infinity. And then similarly for when x approaches positive infinity, as x gets bigger and bigger, so does y. Positive infinity. So it just matches. So again, there's so many no's here, and then the range is like a weird thing. So I'll never test you on this, but you need to know this is a basic BFF. You need to know that it looks like stair steps, and you need to know that it's called the greatest integer function, and you need to know that its equation is this. Cool. All right, let's do sine next. I cannot wait to learn to get to sine. I hate this stuff that we're doing right now. I cannot wait to get to trig stuff. And so we'll start with a sine graph here. And I think it's important that we know some basic things about the sine graph. Sine, the equation for sine is just sin x. I want us to always think of it as sine. So I know it says sin, but it means sine x. So always think sine, 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 sine. Okay, let's go look at my textbook, what that graph looks like. Sine looks like a big wave, and we will study this graph way more in depth later. But all I need you to know right now is that it never goes higher than 1, it never goes lower than -1, and it always goes through 0, 0. So those are the three things I want us to know about sine. So let's go graph it. So sine goes through 0, 0, and it will never go higher than +1. I'm just going to put a little highlight so that I know when I'm graphing it doesn't go higher than that, and it doesn't go lower than -1. Other than that, you can just wave throughout. I'm going to wave. Just wave, wave, wave. We'll learn later how to make it really pretty. I won't count you off as long as you show me that sine goes through 0, 0. The reason I'm making such a big deal about that is because cosine looks exactly like this, but it goes through 0, 1. So cosine is wavy too, but cosine doesn't go through 0, 0, it goes through 0, 1. And then it has all the same rules. So it doesn't go higher than +1, it doesn't go lower than -1, and it waves from here. So look, you got a little bonus cosine graph action in here today too. You see how like from a distance they look like the same graph? That's why I need you to show me that you know it's sine because it goes through 0, 0. Okay, so let's do domain. Domain. Are there any holes in this graph, or are all the x's okay? All the x's are okay, right? Everything's good. There's no holes. Range. Ooh, I do have a tight range though. What does it have to be in between? What did I tell you it has to be in between? 1 and -1, and it can be 1 and it can be -1, so we're going to use brackets here. -1, +1.
So how do you know it's -1?
Because I'm telling you that right now. And we will spend so much more time doing science, I need you to like recognize what it looks like now. Right. So just if you're like, yeah, Ms. White said that, later I'll tell you exactly what. But for now, it's just because I said so. Continuity, is it continuous? Yep, it's a nice pretty wave. It actually looks like the most continuous one. For increasing and decreasing, I will not ask you to write anything there. Because what happens is it is constantly increasing and then it's decreasing, and then it's increasing and it's decreasing. And it does that at very specific points, but I don't need you to know those specific points yet. I will ask you to know that second semester, but I don't need you to know that yet. You can just write yes if you want to there, but I will not ask for like the interval where it's increasing and the interval where it's decreasing. All right, symmetry. I know that it doesn't look symmetrical, but I want us to write yes there. And we're going to say yes, and we're going to say about the origin. When I say about the origin, the symmetry that we're like most familiar with is like about like the x-axis. Like remember the other day when I graphed like the quadratic, and it was like if I could take this off the board and fold it at the y-axis, it would make like a beautiful picture right on top of each other, right? When it's about the origin, that's when it's something like a cubic function where it's the same thing in quadrant 3 as it is in quadrant 1. So if you see a graph that's the same thing in quadrant 3 and quadrant 1, then we call that symmetrical about the origin, and that's what this sine graph is kind of giving us. Again, I know that, which is why I'm telling you that right now. And you can write it down and then learn it that way. Have anybody questions about that? Okay, boundedness. Is this bounded above? Is there a point we can never go above? Is it bounded below? Is there a point we never go below? Then we say it's bounded both. We're going to say bounded both above and below. There are no local extrema or absolute extrema because it hits 1 and then it comes back down to -1. We're just going to say no for these. Now, we might think because it's bounded that we have asymptotes, but that's not true. We're not approaching anything. We just never go above or below a certain point. So there are no asymptotes here either. And then I will not ask you end behavior on this because it's just always going to be in between 1 and -1. So you don't have to do it. You can just write NA for end behavior. Same thing for cosine. I don't want end behavior on cosine either. Awesome. Okay. All right. Does that help a little bit? Give us a couple more examples for when you go home and do this later. Again, I want these all filled out by Tuesday. I do have office hours on Monday morning if you need any help, or if you can email me or ask me whenever if you have any other questions. But I do want to check on Tuesday and just be like, flip, flip. Okay, you did them all. All right. Okay, let's go back. Let's go back to our notes. We're going to finish 1-1. If we get to, we'll start 1-2. We'll go to lunch at some point. We'll get moving on 1-2. I do not anticipate finishing 1-2 today, but I guess we will find out what happens. Okay. We got all the way through 47, right? So we're on number 2 on our 1.1 notes, correct? Okay. So these first 2 are just solving algebraically. So we're just going to do a little throwback to algebra. We're going to combine our like terms. When you have like an x squared and an x, let's move everything to one side and then kind of see what we need to do after that. So I'm going to move everything to this 2x squared side. So I'm going to minus x squared plus 3x minus 4 minus 4. That gives me x squared minus 4x minus 12. Once I get here, there's a ton of ways I can solve this. What's one way I could solve this? Quadratic formula. Perfect. What's another way I could solve this?
Factor.
Factor. What's another way I could solve it? Complete the square if you're feeling crazy. I did say algebraically, so graphing is not an option here. So those are 3 great options. I think factoring is actually the easiest one here because I don't have a number in front of my x squared. And so I'm essentially asking myself, okay, what numbers multiply to be -12 and add to be -4?
Plus 2 minus 6.
Good. There we go. Which makes x equal what? 6 and -2. Perfect. Awesome. Okay. That wasn't too bad. Same thing for the next one. I want to distribute that x, and then I want to bring the 14 over to the other side, and then I think we have the same two options as well. Same three options. Quadratic formula, complete the square, factor. We'll see whatever works the best, okay? So let's distribute. I get x squared plus 7x equals 14. We'll bring that 14 to the other side.
I left something in here. Can I go get it?
Yeah, I wondered why there was kids just standing outside. Yeah, you're welcome to come in. Do you see
I don't know
it?
if I saw it or not.
Oh, okay.
Or whatever. Okay.
Oh, you left that here last Friday.
Yeah.
Okay, I was gonna say I've had that for a while. Bye.
Yeah.
You guys know what that kid is? Never seen that kid before. There's this like random bag that had like a name on it, but it said like a girl's name. It said like Polly or something. It was like a weird name on like that back desk. And so then I put it over here, and it's been a full week and nobody's grabbed it. So that's just weird. Anyway, okay. All right, now that we're here, what should we do? Can we factor this? I think probably the best is quadratic formula. After that, you can complete the square, but I don't want to if I don't have to. So I'm going to do quadratic formula. So I'm going to do x equals negative b plus or minus square root 7 squared minus 4 times 1 times negative 14 over 2 times 1. But can you take your Apple Watch off? My friend taking his test, yeah, you shouldn't be wearing that.
It won't even connect to my phone, so.
Perfect, then you don't even need it. All right, so now we are going to solve. I'm sure you guys can kind of do that on your own. I'll just walk through it. 4 times 14. Plus 56. And then I have this 105 under my radical. Can I simplify 105? 105 divided by 5 would be 21, and 21 is 3 and 7. So no, that's as good as it gets. That's a fine answer. All right. Cool. So we did a factoring one. We did a quadratic formula one. Anybody questions yet? All right, and then the last two say solve graphically with the calculator. We actually did this back in Unit P, where we graphed 1 in Y1 and 1 in Y2, and we saw where they connect. So let's do that. Go get your graphing calculator. Let's put those up, and I will reflect it on my screen as well. Right.
I want to say it was. I know.
All right, you guys all remember how to graph square roots in your calculator? All right, once you graph them, let's see where they intersect at. They're kind of ugly. Let me go fix my window. Do they intersect at one or more places? Just at one place, right? It's kind of a funky graph, but let's go figure out where that point of intersection is. Square roots? Oh, yeah. Sorry, I'll go back to Y1. So I put like one of the sides of the equation in Y1 and one in Y2. And then I just got it. Left bound, here and left bound, here and right bound. All right, so mine says that they intersect at the point 2.66, comma 2.94. Which of those do I want, the X or the Y? X. Don't give me an ordered pair. Like I need you to know, especially at this point, we were solving for X. So I just want what X equals. And so you can even write that, right? Like X equals, and then just write the X version. So in this case, it's 2.66 or 2.7. You can round that way if you want. I do not mind. That's it. All right, same idea for the next one. Let's go back. We'll graph those. X plus 1, x squared minus 2x, minus 5. No, this time it looks like they intersect at 2 places, so we're gonna have 2 answers here. So I get negative 1.37 and then positive 4.37. Does that look right to you guys? Or did I do that wrong? Okay, good. Yeah, and that's it. It just wants us to find the points of intersection. It wants us to find where x equals, and so that's it. Right. That is the end of 1.1. So we still have a few minutes before lunch. I really hate this new lunch thing because I would normally just send you to lunch right now. But they like do this weird clean of the cafeteria, don't they?
No, they're mean. They kick you out.
Yeah, they kick you out. So like if I send you now, would they like make you leave then? No, you're fine. Okay, let's do
I
that.
think it's fine.
Can you come back at 12:10 then?
Yeah.
Okay.
Okay.
That's 30 minutes. I'll see you at 12:10. That's when the lesson's starting. Bye. Andrew, you're free to go off of Zoom and then come back at 12:10. That's in 30 minutes. Or you're welcome to just stay on. I'm just going to mute us in here, okay?